Good afternoon. So today we're going to talk a little bit about gravitational potential energy and escape velocity. In order to motivate that discussion, I have a little scene from the movie Interstellar. Now, if you've never seen the movie, it concerns some astronauts exploring around a supermassive black hole. There are some planets in orbit around this supermassive black hole, and they're exploring these planets and hoping to find a new home for the people of Earth. They've found one planet and it's not at all hospitable to them, so they're going to try to escape from this planet. But there's a lot of gravity on this planet and it's orbiting around this supermassive black hole, as I said. So they are going to have to use every ounce of engine they can provide in order to escape this planet. Now, this spaceship they're on has the main spaceship, and then there's two shuttles attached to it. And the shuttles each have their own engines. And so they're going to use the two shuttles' engines along with the engines of the spacecraft itself to try to escape this black hole and the planet. They're actually using the gravity of the black hole as an assist here. So once they get going fast enough by using the gravity of the black hole, then they're going to fire all their engines and try to see if they can escape from the gravity here. So with no further ado, let us watch this little scene from Interstellar.
It's what we intended, Dr. Brent. It's our only chance to save people on Earth. If I can find a way to transmit the quantum data I'll find in there, they might still make it.
Let's just hope there's still someone there to save.
Prepare to fire escape thrusters. Ready?
Ready?
Ready. Main engine ignition in 3, 2, 1. Mark. Lander 1 engines. On my mark. 3, 2, 1. Mark. Ranger 2 engines. On my mark. 3, 2, 1. Mark. This little maneuver's gonna cost us 51 years.
You don't sound so bad for pushing 120.
Lander 1, prepare to detach. On my mark. 3, 2, 1. Mark. Detach.
Goodbye, Taj.
Goodbye, Dr. Brent. See you on the other side, Coop. See you there, Slick. Okay, Case. Nice reckless flying. Learn from the master. Ranger 2, prepare to detach.
What? No! No! Cooper!
3,
Cooper, what are you doing?
Limbs third long. You gotta leave something behind.
You told me we had enough resources for both of us.
We agree today. 90%.
Don't.
Detach.
Alrighty then.
Stop. foodie-dooey holiday shopping this year, you really have to see this. I'm going to show you one simple trick that'll save you a lot of money when you're shopping online. In fact, I was able to save $350 this month shopping online.
Find the
using
pause
exact
here.
same trick I'm about to show you.
Have to
Watch
do it.
this. I can show you how to get the sweetest deals online when you shop from major retailers like Amazon and Target. You can drop prices automatically. I can show you how, but I can't do it for you. People are saving real money doing this, 160 million in the last year. Across thousands of different retailers, you'll immediately see this. See what I mean? You'll see better prices you have no idea.
And we'll switch over to the other screen here. I can't seem to find the mouse there. We'll just turn the volume down there and let it run if it wants to. So, a couple of things about that little scene. The black hole images are actually accurate as far as we understand it. One of the producers on this movie, one of the people that wanted to get it made, was a person by the name of Kip Thorne, who literally wrote the book about black holes. He actually won a Nobel Prize in 2016 for his work on gravity waves, detection of gravity waves. But he knows a lot about black holes, and he wanted to make this movie, and he tried to, as best as possible, within the limits of the Hollywood system, to make it show things accurately. Like, for example, in the black hole there, you don't, when you see a black hole, you don't just see a dark spot in space. As you may know, a black hole is something that has so much gravity that it can't even, light cannot even escape it. But that doesn't mean it's dark. For one thing, there's an accretion disk around it, debris and things that have been sucked up by the black hole's gravity, but they have not yet fallen into it. And then there's also light from behind the black hole that gets curved, because the black hole's gravity is so strong it actually curves light as it passes by, and that's why we see, light coming from, what looks like it might be from behind the black hole. Actually, you can see it in front of it. They've actually have now done pictures using a gravity lensing technique that also involves the bending of light when they go around stars or black holes. And they've a computer-generated image of what a black hole would look like then is pretty close to what you see here. This has obviously been embellished quite a bit, and a lot of the textures put into it, but the basic idea, what it looks like, is kind of the same. Anyway, what I want to focus on was this idea of trying to escape something, trying to escape this force of gravity. So, here's the idea. We know that when we talked about the force of gravity, and we got a formula for the gravitational potential energy near the surface of a planet where the gravity field strength is a constant. And then we said, imagine you have something that is being thrown up into the air. We said that the change in gravitational potential energy is the work done on that thing, the negative of the work done on that thing by the force of gravity. So the idea was this. Let's say I give Ratbird a certain amount of kinetic energy. I start throwing him up. As Ratbird rises up through the air, gravity is doing negative work on him. Gravity is pulling down, Ratbird is moving up, and so Ratbird is losing kinetic energy because of that negative work. But where's that energy going? Well, it's becoming the potential energy. With functions like gravity, forces like gravity, we can define a potential energy function that gets bigger as that force does negative work on the object. So as Ratbird rises, Ratbird loses kinetic energy and gains potential energy until such a time when Ratbird rises to the top of his path and he has no kinetic energy left. At that time, he's still in the gravity field of the Earth, so he's going to start falling back down. What if I throw Ratbird up even faster? And you won't be able to see it because you go up way too high. But if I threw Ratbird up faster, then he'd take longer. He'd get away farther before he reached the point at which he has no kinetic energy left, and he'd start falling back down again because he's still in the gravity field of the Earth. But what if I could throw Ratbird such a fast speed that he'd get all the way beyond the gravity field of the Earth and still have some kinetic energy. That means the rapid would still be going up. When he gets to that zero of kinetic energy, he's not going to fall back down because he's away from the gravitational field of the Earth. Now, let's figure out how much that velocity needs to be. First, we need to modify our formula for the gravitational potential energy. Before, we just worked out that it was mgh because we took mg as being the constant force of gravity acting on something, and h is the height to which it was lifted. We said that that was the change in gravitational potential energy. But we can't do that here because now we're talking about going really far away from something where the force of gravity changes. It's not just a constant g. So in that case, let's go back to first principles. The change in potential energy is equal to the negative of the work done by the force. So it's the work done against the force or the negative of the work done by the force. Well, if this is the force of gravity, and ds is a little bit of the path that our object is following, then a negative f times ds dot ds should be the little bit of potential energy change that that thing undergoes. Well, what's the force of gravity going to be? Let's say we're talking about just following a radius. Like we have an object moving along the radius. And it doesn't matter, by the way, what path we take, because that's one thing about a conservative force. It doesn't matter what path you take to calculate the change in potential energy. It's going to be this, just whatever the final position is and the initial position. The change in potential energy only depends on those two things. But the formula for the force of gravity is g times the mass of the Earth. We're talking about the Earth, escaping the Earth, times the mass of the object, divided by the distance between the Earth's center and the object squared. And then a minus in front of it because, by definition, the radius vector, it's pointing outwards. So the direction of the radius pointing outwards, and so this force then points inwards along the radius vector, back towards the Earth, and so that's why it's a minus there. But that minus and this minus cancel out, or make each other irrelevant, and so we're left with is just g times the mass of the Earth times the mass of the object over r squared dr. So that is a little bit of change of energy that we have, and if we are trying to calculate the total potential energy difference between 2 points, then we would integrate that over our path. And so, if you integrate 1 over r squared, you get a negative 1 over r. And we're just going to integrate it from some initial position to some final position r. And so this is going to be a minus g times me m over r, and then plus some initial potential energy depending on where we start. Now the usual thing to do is to use this formula, but to say we're going to start at an infinite distance away, where the force of gravity is 0, and the potential energy should be 0 out there. That's where we're going to set the 0 potential energy at an infinite distance away. So if we are saying that our infinite distance away is our where the potential energy is 0, well, at infinite distance, this term would be 0, so that means that u naught must also be 0. So our formula for the potential energy of gravity is this. Potential energy of gravity, where u is 0 at infinity, is a minus g times the mass of the Earth times the mass of the object over r. Now, what happens to the energy as the object approaches the Earth? Well, remember the potential energy should get smaller. But is that the case here? as r gets smaller, this quantity would get bigger, but it's negative. So it still satisfies our idea that r has to get, the gravity has to get, potential energy has to get smaller as the distance gets smaller. It just gets more negative. And this formula is only derived for where the force of gravity was given by that earlier formula. So inside of the Earth, we're going to talk about what happens inside of the Earth, but we can't use that formula. We can only use it up to the surface of the Earth. Because inside of the Earth, we're going to learn in a couple days, or actually tomorrow, the force of gravity decreases as you get closer to the center. And so this allows us to calculate what we want to calculate. If we want to know, do we have enough velocity for something to escape the pull of the Earth's gravity, what we are saying is, like Ratbird here, if I kept throwing Ratbird up faster and faster, we were looking for the point where his initial kinetic energy plus his potential energy at that point was enough so that when Ratbird gets all the way up and his potential energy is zero, he still has some kinetic energy. In other words, the minimum condition would be when Ratbird gets so far away from the Earth that his potential is essentially zero, that's where you want him to have zero kinetic energy. So at that point, the kinetic energy plus potential energy will add up to zero. But since mechanical energy is constant in a closed system here, have no non-conservative forces, that means the kinetic energy plus potential energy must equal zero here on the surface of the Earth. So the condition for having escape velocity is to have a total mechanical energy above zero, which means when you get a very far distance away and your potential energy is zero, your kinetic energy is still above zero. Or the limiting condition is exactly equal to zero. So in order to have escape velocity then, we need to write the total energy is going to be the potential energy, which is a negative g mass of the Earth, mass of the object over r, plus 1/2 mv squared, and this has to be greater than zero. That's what we want. Or if we make this the escape velocity, we can say it has to equal zero. Say this is the escape velocity. Then what we're saying is that that velocity has to be such that the total energy is equal to zero, which means you get far away from the Earth where the potential energy is zero. That's where your kinetic energy is also equal to zero. Okay? So this should equal zero. Well, this is the escape velocity. All right, so that means that 1/2 m the escape squared is equal to g, bring this over to the other side of the equation, makes it positive, mass of the Earth, mass of the object over r. And you'll notice the mass of the object doesn't matter. Escape velocity doesn't depend on how much your mass is. You could have a heavy object, a lighter object, their escape velocity is the same. We're trying to solve for this, so we're going to multiply both sides by 2. This gives us escape velocity squared is equal to 2 times big G mass of the Earth over r, where r is radius of the Earth. And if you take the square root of both sides, this is the formula that you get. So there's our escape velocity. That's how fast something needs to be moving at the surface of the Earth so that it will escape the pull of gravity. Now you might say, well, does it have to be pointing in a certain direction? Not really. It doesn't really matter because, you know, the Earth is more or less a sphere, so any direction you're going, happen to be going, you're eventually going to be going away from the Earth. And so that's the escape velocity that you need. Now, what if your velocity is less than that? What's going to happen? Well, it means eventually you're going to come to a point where you're going to run out of kinetic energy, and you're still in the Earth's gravity well, still in the Earth's, feeling the pull of the Earth's gravity, so you're going to come back towards the Earth. And if you have some horizontal velocity, well then you're going to be going in an ellipse. You're going to be going in a path, a closed orbit of some kind. Most generally, it's going to be an ellipse. You're just going to be having some velocity out there that is not fast enough to escape the Earth. You're going to start falling back down before you get far enough away. And so that's what puts you in a closed orbit. And what if you do have more than that? Well, that means you're going to get all the way from the Earth, so you're not going to come back. So that is going to be an unbounded orbit. So our categories are, if the object's total energy, kinetic plus potential, is greater than zero, that's going to be an unbound orbit, or we can say if the orbit is hyperbolic. Hyperbolic in the sense that if this is your object here, you know, it's going to just kind of pass by and keep going. If your total energy is less than zero, that's when you're going to have a bound orbit, and it's going to be an ellipse. Assuming that only one object is gravitationally attracting, which is, you know, not the real. It's not the real situation. We have other objects, so it's going to make the orbit more complicated than that. But there you go. So tomorrow we're going to look at, this here was all predicated on the idea that we're exploring the gravity as you get farther away from the Earth. But what happens if you go inside the Earth? You know, what's the gravity like there? We're gonna cite a result that we're going to be able to apply, and then we're going to try to figure out what the gravity would be if you were inside of a hollow shell, what the gravity would be if you're inside of a solid sphere that was uniformly dense, and we're even going to calculate eventually how long it would take to fall through a hole drilled through the center of the Earth, assuming that, you know, one could survive such a trip, which is unlikely. We're going to talk about how long it would take to do that. But that's all to come up tomorrow.